Here's my wired attenuator board. This is what its schematic looks like, or layout I should say. You see the 12 volts goes through to the 12 volts to the transverter board here through a switch. The switch is right there. And the push to talk goes through to the transverter board push to talk, and also these relays are switched by it. And that's this guy right here. And when there's no power, then these relays connected to the HF antenna directly. As soon as I turn on the DC power here, it will switch directly over to the IF here to receive IF output signals without using the attenuator, obviously. And once I ground the push to talk, it will also ground the transverter board push to talk line. And that will make it go through this attenuator and also the attenuator that's on the transverter board for transmit purposes. So that's the basic scheme, what's going on here. The implementation, as I said, this is the HF in, there's the HF out. Here's the transverter IF in and out. The relays, the attenuator, push to talk line, the power switch. And right now you see there's two LEDs on the board here, one here and one here. Those are presently inactive because there's no power to this board. If I turn the switch on here, however, you notice that the red LED comes on here, indicating that there's power to the board. So now we have this connected directly to this instead of this, so that the receive signals come through without any attenuation in here. As soon as I ground this, you notice that another LED comes on, a green one, saying that it's set up for transmitting. And when that's the case, it goes from this through the board to there. Let me illustrate that without having it on. So it goes from here through the attenuator to the transverter. Now this cable is long for a reason. I have this connected to here so I can do some testing, which we'll do in a minute. Ultimately, this will go down to the transverter board on the bottom in the other half of this arrangement. And this will become the 222 output port. These two wires, of course, are the feed wires that feed the push-to-talk brown here and the red B+. So those will also go down to the transverter board and be connected in the appropriate place. So that's basically how I got this thing wired. What I will do is turn this over, show you the other side. First I'll turn the switch off. And this is what it looks like on the other side. I have a switch here, the RCA jack here, the BNC connector here. This is the power. This is, which one is that? That's the HF, and this is the VHF or UHF, whichever you wish to call it. I guess 220 would be still be VHF. So that's how I happened to implement this thing. I did make one error, and that is that, as you notice, this crossover here of things, this should have been put here with this, and then the wires would have gone right straight to there. And this should have been put here so that this could go directly to it. But that's not what happened, so next time around. So that's the only real kerfuffle I made here on this one. Oh, I also should mention I had to take this nut off. Well, it looks like it's loose. I'll have to tighten that more. Anyway, to make it easier to solder that wire in and that wire in, and then tighten it down again. It doesn't short those out, but I wanted to make sure. Probably should have used a nylon washer there, but I don't happen to have one for a 440. But it's okay the way it is, and I'll just tighten that thing down and we'll be fine. Then we can test this thing. As a preliminary test, I thought what I'd do is use the continuity function on this meter. As you see, we can both measure the impedance and listen to a tone. If I put this on ground here and go to any of these grounds, I get a signal. But I don't get anything on here, which I shouldn't. Nothing connected to those. If I go from this one to there, since I have no power, it's connected, but it's not connected to there. Oops, excuse me. Which is the way it should be. And if I turn this switch on, you see the LED light, and this one now doesn't go to here, it goes to here. So that function is working. And if I was to ground this, I would get some kind of resistance between here and here. I don't know how much, I'd have to calculate that, but I'm not going to do that because I don't have enough hands. But anyway, so I've checked to see that the function is actually working on this thing, and that's the key issue there. I've normalized the tracking generator here through this barrel, and then back into the spectrum analyzer. It looks like we're at 0.01, 01, 01, and 01. So we'll take it off of the barrel here. Put the tracking generator into the transceiver port, which is what it represents. Use that to sort of hold this thing up so we can see it. Put this on the HF port, which is this port up here, which has a 0.05, 05, 09, and 0.14. So that's pretty good. I can't complain about that too much. So this is switched off here, and we have very little loss between these two. If I switch it on, however, you see that we get some isolation there because we've now switched this port over to this port, and this one is isolated, and it looks like it's 35.8, 34, 30.3, 27.7 at 21 megahertz, 28 megahertz, 52 megahertz, and 70 megahertz. Not sure anybody in Europe would use 70 megahertz because their bandwidth is limited there, but it is possible, I suppose. But anyway, we are, of course, at 28 because that's what the kit comes as. And so that's the band that we'll be passing. And then if I, we'll do one more test here. What I've done here is I've grounded out, you can see the wire coming around here, this RCA jack on the back. And so you can see the isolation here is about 50 some odd dB from this port to the HF port, so that if you're on 220 you wouldn't be radiating very much out there. Even if you had 100 watts here, you'd only get 0 dBm out of here, and you're supposed to not go over 10 watts or so. So you're not going to get much out of this port. So that's good. Let's see what our isolation is to the from the transmitter port here, transceiver port I should say, to the to drive the transverter in the TX mode here. And it looks like it's right at 30 dB. Let's see how close it is on all of those. 30, 30.2, 30.5, 30.2. So a very flat line at that particular level. And let me see if I can get in here on the back and run this pot down. Still stays pretty flat here till we get to 40 dB, and it starts changing a little bit. And we can get down to 50 dB or thereabouts, except at the 70 megahertz range there. So that's pretty good. So we have a pretty good adjustment range on there, and fairly flat, at least up to 70 megs. 100 megs you start losing it, but there's really nothing up there you'd be using to drive this thing anyway. So we're good in the 10 to 100 range, and certainly good in the 10 to 70 megahertz range for the attenuator board. So I'm happy with that. Oh, let's switch this again. There's your isolation when the thing's turned off again. So you're in the same category as before: 37.7, 35.7, 31.3, 27.9. So about the same isolation from this port to this port when you switch to this port by turning this off. Okay, I've finished up the wiring here from this board to this board. We have the IF output going to the transverter going into here. This is the brown wire, which is the push to talk off this RCA jack over here. This is the red wire, which goes over here and is the feed of the 12 volts across to this board. And this goes back to this connector, which we had been using for testing purposes, which is now marked 222 because this is now the 222 output from this power amplifier here. This jumper, as it turns out, is there for checking the transmitter to see what its current is, I presume. So it's available for that purpose, probably to set the bias on the thing. And I believe this is the power pot, and this is the bias pot, so I probably need to make sure I've got that set correctly before I turn on the transmitter, that is. And he does not give instructions on that, and I did turn that pot thinking it was this pot. So now I've got to try to figure that out. Well, I have to say that I have had a little lack of progress on this unit, and primarily it's because, well, if I go between these two screws, which are screwed into the edge here, I have continuity here. If I go from here to here, as you see, because this is anodized instead of alodized, there's no conductivity, which is fine if you have a transistor that doesn't want to be grounded. I've scraped away a little bit here, which helped the situation. And over there, of course, I do have continuity, but it also leaves a rough surface, which doesn't give the best thermal properties. Not sure that the thermal compound I was using was all that great for this situation either. But anyway, I did test it after I was only getting well, less than a watt, and now I have about a watt to 2 watts somewhere in that region with this situation, but I don't think that's ideal because I roughed around here, and this is really the area I should have, which is where the actual center of the thermal contact needs to be. But anyway, if I take a regular heat sink, for example, one that I just bought like this thing is well, that one's also insulated. So this has a finish on it as well, so you have to be a little careful on that. But if I go in here and here where it's been drilled, I make contact. So the only contact I was making on this unit was probably through the screw here and that to the ground there. So that's a problem. But what I've done is I've gone to a heat sink that's just aluminum here. And as you see, it's got good contact. And I can go from anywhere here and get good contact. So this should work. Whereas this guy won't work as well, I don't think. That's the theory. And that's why this one won't work as well unless I continue on this out here in the area where the actual heat is generated on this TO220 transistor that's used here. So I've got it wired up here to see if we can prove that point. I mounted this on a heatsink here, and the heatsink here, I have no grease under this part. With no drive, this is turned. The drive is turned off at the moment. I've adjusted the voltage here for 13.6, and I've adjusted this pot for about looks like a half an amp of idling current. That includes the drivers and all of this. I'm not using this to just look at the final. What you do is pull this this off, and you would get the current of the final stage itself. That makes this thing a little bit on the toasty side all the time whenever this is connected. When I take that off, it drops down to the receive current, which is somewhere in the neighborhood of about 100 milliamps. If I pull this off, which will eliminate the final, let's see what we got, and push this back on. Okay, I've grounded the TX line now. I have the jumper off, so the final is not in the circuit. And I have about 150, 175 milliamps at the moment without the final on. When I put the jumper on, we go up to, I'm looking at the thing here, it goes up to about 100 or 400, 500 milliamps. So it looks like 350 milliamps in just this stage alone. Don't know if that's correct in terms of what it should be. It's about 1/3 of it what it would be at 1 amp, so it seems reasonable. This is a MOSFET. But anyway, that's what I've got. So let's see what happens when I apply drive to it. Okay. This goes up a little, which I don't understand. Maybe it's detecting some of the RF energy. Regardless, so we're in that neighborhood. And I've got, looks like 2 watts out. If I crank up the power over on the generator, I could probably get that up to 2.5 watts, something like that. But we'll leave it at 2. Now that's with the modulation turned on. So that's actually twice that peak envelope power, roughly. So 2 watts is about 4 watts. And I'll turn the modulation off. You'll see that meter go up. Okay, and the meter's gone up to 4 watts. So that's exactly what you'd expect to see, is something in that neighborhood. So this seems to be working good now when it's on this heatsink. It did not work very well using this as the heatsink. And I believe the reason is that this is anodized. This finish is not aluminum. This is anodized, which is a non-conductor, number 1, and not the best thermal heat transfer, number 2. Now I did make an attempt here to, don't know if that's going to show up or not, but to scrape that away. But I only got about 2 watts, 2.5 watts maybe. And, but I didn't probably clear enough area here to get the chip to be exactly over where the clear spot is, both for thermal conductivity and for heat conductivity from the tab. The tab was probably all right because this area is contacted, but down here where the chip is, where the heat has to come out, it's not clear enough. So I'll probably do that as another experiment. This is a little thinner than this is, of course, and that makes some difference as well. So if you're going to build in this box, unlike what I showed earlier, I would put a piece of aluminum here that has no plating on it like this does, and use that as a heat sink. So just tie it to the base here. You can go to most hardware stores and get sheets of aluminum that are about 1/10 of an inch thick by maybe 2 inches wide by a couple of feet long. And if you cut a piece of that off and put it in here for the heat sink, that might do the job for you. Otherwise, you might want to get a piece of heat sink like this, but make sure that it's a good heat sink, because frankly, this does not have any conductivity. If I put a probe there and there, I'll see nothing. If I go to these screws, which are screwed into the material here, it breaks through the anodize and picks up the contact. So from here to here I'd get a continuity, but from here to here I wouldn't. Allodyne products, which are the sort of goldish color, also will have conductivity and good thermal properties. So you could use an allodyne piece of aluminum or something for your heat sink. But apparently this does want a heat sink. Now, we've been sitting here transmitting for a while, and we're still at 2.5 watts, a little bit more than 2 watts, 2.4, something like that. And if I put the modulation back on, as you see, we go down to 2 watts. So, and this is, yeah, it's getting pretty warm. It's getting pretty warm, but not so hot that I can't hold it. Probably a little over 100 degrees, something like that. So that's the key for these parts apparently to work, is to have them well grounded and well heat sunk. So if you're going to build this kit, you're going to have to do something like get a heat sink, or in some way modify this case so that you have an area cleared around the hole that this thing's mounted on, making sure that whatever you scrape away, that gets flattened out, either with steel wool or something, to give good contact all the way through to transfer the heat, or possibly a little bit of the heat sink compound on the thing, very, very thin, a lot thinner than I showed you, might help fill in the gaps and allow the transfer of heat into this thing.